Hi students. So today we are starting lecture 67 and today we are going to spend a few slides from now on discussing about structures and materials. So essentially we have been looking at the different aspects as far as aerospace engineering is concerned, such as the aerodynamics, the flight mechanics, the space mechanics and so on. And now we are going to spend some time looking at the structures and materials because at the end of the day the lift and drag have to be transmitted onto the body, and the body must be something which can handle this kind of force which acts on the body. So that's the subject of the aircraft structures. So let's start with some very simple members which are considered in subjects such as strength of materials and mechanics of materials. For example, let's look at the axial rod. So essentially, if you have the axial rod, you can subject it to some forces here. So I have put the force F here, and let's say that this rod has a starting length of L. So what happens is that if I put this kind of compressive force here, this body is going to get compressed, the length is going to reduce. So this is essentially known as a deformable structure. Now, when the length reduces, this reduction is the amount delta L. Now we can define a parameter known as strain. So we use the Greek letter epsilon to denote strain, and this is given as delta L by L. So that's the extension, or rather here the compression divided by this length L. Now, essentially, if we assume that this body has a cross section of A, then we can write sigma is F by A, and that is stress. So this is the definition of stress. You will see it's somewhat similar to the definition of pressure. And now we also have the definition of strain. So these quantities are simplest when you look at a one-dimensional problem or a unidirectional system, which we are looking at in the case of the axial rod. Now, if we were to take the same axial rod and put this in tension, what would happen is that the starting length would be L, and then the length would increase by some amount delta L. So here we have an extension type of scenario. So in this case, again, the strain epsilon would be delta L by L. That is the extension divided by the starting length, and the stress would be F by A, which is related to the area of cross section, in which case this is a circle here. So A would be pi r square. Now this is the basic and fundamental definition of stress and strain, and these kind of structures are good if you want to carry axial load. So that's one of the fundamental loads which you need to carry in any structural mechanics system. So now let's look at these two formulas. One is the formula which is defining stress, and the other is the formula defining strain. Now if you look at these two equations, they are totally driven by the geometry of the system and the force you are applying. So the geometry of the system is L and A, and you are applying a force F, and so you are getting this delta L deflection which is present because of the force F. So there must be some relation between stress and strain, because if I apply more force, stress would go up, and so strain would go up. That's something which we know from our intuitive knowledge of any structure. Now this relationship is at its simplest form given by sigma is E into epsilon, that is stress is E times strain. Here E, which is the constant here, the constant of proportionality, is the Young's modulus. It's a material property of any given material. So if we perform tests on different material in the linear region, we are going to encounter this particular relationship. Sigma is E into epsilon. Now this is known as Hooke's law, and this was propounded by a scientist with the name Hooks. It's there in many physics books and so on. So if we actually do an experiment of a typical metal, we can get the stress strain curve. We can plot sigma versus epsilon, and we get a curve like this, which I have shown in the red line here. Now you will see that in this linear region, this relationship sigma is E epsilon will hold, and then after some time you will encounter something known as the proportional limit. So this is the point where linearity ceases to be there. Now this region is known as the elastic region because in this region you can move back and forth here. But once you start moving into this region, you are encountering this kind of nonlinear behavior. So what will happen is that you will go up further, you have a certain point known as the yield stress, then ultimate stress, and then finally fracture of the material and its complete destruction. So this region from the proportional limit to the fracture point is known as the inelastic range. Now let's look at some of these definitions. So we can see here that when epsilon is greater than the proportional limit, the permanent deformation or set starts taking place. And when this permanent deformation is 0.002, that is the point where we say we have the yield stress. So that's the essential definition here. Now, of course, for our structural mechanics work, we are going to assume that we operate in this region, and that's going to make our life very simple, or at least our life relatively simple compared to if we wanted to do a more complex problem here, because remember here you are getting permanent deformations and so on, which is not something which you want to get in any structure. So what you want to do is that you want to design the structure such that the stresses remain in this particular region. And you can do that by, of course, working with the cross section of the particular material you are dealing with. So you know a certain force is going to act. You can work with the A there so that sigma is F by A is appropriate. Now let's look at certain structural members which are widely used. So let's start with the axial members. And axial members are essentially like the rod I showed you before. They are used to carry tension or compression loads, and in the case of axial members you have the simple formulas which apply. So sigma is F by A, that's the stress. Sigma is also E into epsilon, that's the Hooke's law. And so I can write F is A into sigma from this equation, and then I can write this is equal to EA epsilon from this equation here. So this is an important relationship, and from this relationship we can see that the axial member can carry the same load F if EA is the same here. So EA is a parameter which is very important. So what happens is that let's say these are the different cross sections which are available to you. You can choose any cross section as long as EA of this cross section is the same. The particular load F can be carried here. Now one of the problems which happens in axial loading is when you actually compress the rod, and when you compress it, it's not only that it goes through strain and after a certain point it may fail, but there is also a phenomena known as buckling which takes place, and because of buckling you can sometimes fail at a stress which is greater than the ultimate stress in compression. So something which needs to be considered in axial member design is the possibility of buckling. So that's very important. Now let's look at the shear panel, and shear panel is a thin sheet of material which can carry in plane shear load. So here I have shown a typical thin sheet of material. So you can see the dimensions are A and B, and the thickness is T here. The X and Y axis are shown here. So what happens here is that these stresses tau are generated on this sheet of material, and these are known as the shear stresses. So in this case what happens that the shear force is given as Vx is T into A tau. So you can clearly see here in this particular side, T into A is the cross section, and when we multiply it by the shear stress, we get the force or the shear force in this direction. And this can be written as G gamma TA because we have tau is G gamma. So this is an analog to the Hooke's law, and this exists for the case where shear stress is related to shear strain. So here tau is the shear stress, gamma is the shear strain, and G is known as the shear modulus of the material. It is another material property which you can derive by experiments and some theory. Now let's look at the next structural member, which is the beam, and the beam is used to carry bending moment loads. So essentially if we have a beam, we have a bending moment which acts on that, then the beam is the suitable structure to carry it. Now of course you'll see the beam can also carry axial load because it does look somewhat like a rod, and both these loads are something which can be carried by a beam, but the bending moment is the one for which the beam is explicitly designed. Now, if we look at the typical formula, which you may have studied in strength of materials for a beam, its M is minus EI d2W by dx2. So here this relationship becomes very important. It relates the bending moment which has been applied to the deflection W, and EI is the bending stiffness of the beam. Remember, E is the Young's modulus, which is a material property, and I is the moment of inertia of the cross section. So if we have a rectangular cross section, for example, with dimensions B and H, then I would be BH cubed by 12. So this is a very fundamental equation as far as beam theory is concerned, and it's something which we often use when we are looking at beams. Now, beams are very important in aircraft structures because the wing can be modeled as a beam. So what happens with the cantilever beam is that it's fixed on one end here. So for example, typically the aircraft wing is fixed at the root, and at the second end it is free. So this is also known as a fixed free boundary condition, and when that happens, that particular beam is known as the cantilever beam. Now if we were to look at this formula very carefully, we will get certain insights. For example, let's say we have fixed the material, so E is fixed, and we also want the same curvature to exist. Then what would happen is that if I have a higher level of bending moment, then a greater value of I would be able to support that bending moment. So that's something which we again need to consider. And one of the things in bending of beams is that it is not just dependent on the area A, it is now related to I. So I, if you remember from basic physics and so on, will depend on the cross section. So for example, if we have a particular cross section here and here and here, the I values of these cross sections would be different even if the A values are the same. So for example, these two may have the same A value, so B into H may be same, but the I value of this cross section may be more because BH cubed by 12 would be more here, H being more. Similarly, if I have certain sections, for example, the I section, this would have a higher value of I because you can clearly see that the parts which are here are going to contribute more, and if you use the parallel axis theorem to calculate I for this particular body, you will certainly find that the I value will be more. So very often in design you tend to place more of the material away from the neutral axis so that you can exploit more of the bending capability of the beam. Now one of the problems with using this kind of structure or thin wall structure or I sections is that you encounter certain problems such as related to transverse shear. So transverse shear starts becoming important, and whenever you study aircraft structures, you spend a lot of time in studying transfer shear also because that's something which is important for aircraft structures. Now let's look at the last of the load carrying members, which is the torsion member. And torsion members basically carry torque. So for example, if you have studied strength of material or you know something about mechanical engineering, you know that cylinders like this are often used to carry torque, and so shafts and all use cylinders like this. So for example, if we were to consider a hollow cylinder here, we put up some reference system X, Y, and Z. We have a torque here, and the cylinder has dimensions A and B. So A is the radius, which is the inner radius, and B is the outer radius. Then this shear stress tau acts on this particular body here of this tube or this hollow cylinder. Now, the relationship here we can use is T is Gj theta, where theta is the twist angle per unit length. So, with this formula, we can actually calculate the value of theta. Now, here remember that J is the torsional constant, and for the hollow cylinder, J is actually the polar moment of inertia. So, Gj becomes pi by 2 B4 minus A4, which you can easily calculate, and Gj is known as the torsional stiffness of this kind of cylinder here. So we get an idea that different type of members can carry different type of loads. Now, if we were to design a particular member which can carry both bending, torsion, and axial load, then we would come up with a member like this. For example, the box beam can be used as a simple model of the aircraft wing. Now, you can see here that this kind of box beam can take axial loads, bending loads, as well as torsion loads. It can take torsion loads because it's somewhat like the cylinder section I have shown before. It can take the bending loads because you have more of the material in the further region from the neutral axis, so the I value will be relatively more, and it can also take the axial load, and you may need to put some stiffeners here to take the axial load in a better manner. Now, because the aircraft structures also carry a distributed load, remember the lift, drag, and so on are not acting at any point, but they are completely distributed throughout the wing. What happens is that you may need to put further stiffeners here, like I have put here, to strengthen the structure so that it can carry the different distributed air loads. So now we are getting nearer an actual aircraft structure, so we would have something like a box beam construction, and we would have stiffeners there. But in reality, what you have is you do have the airfoil section. So because you have the airfoil section, this entire structure has to be housed within the airfoil. And so what you have these strong beams known as the spars, the front spar and the rear spar. And then you have the flange, you have the flange which is essentially carrying certain loads here. And you also have the vertical stiffeners here. So together this entire system is able to carry the bending loads, the axial loads, and torsion loads which act on a typical aircraft structure. So, in general, a multi cell beam is a better model as far as aircraft are concerned than the single cell box beam I showed before. Now let's turn to the material side of the equation. Now, whenever we are thinking of materials, we of course think of metals, we can think of composites and so on. But if you look at the material at a fundamental level, certain properties define the material. For example, density, the stiffness, the strength. And again, here for metals, typically we have an ultimate strength, we have an yield strength, we have the durability and fatigue life in cycles, which is given by N. So what happens is that if you subject a certain material to cyclic loading, it will fail after a certain number of cycles, which is given by N here. We have issues such as damage tolerance, fatigue toughness, corrosion, and creep. So essentially, corrosion is the tendency of the material to oxidize when it is placed out there somewhere, and creep often happens at higher temperature. So it's something which you do not generally want to get. Now, as far as aircraft are concerned, the material of choice is typically aluminum, and it was the widely used material in older aircraft. For example, the Boeing 747, 80% of the structure was designed with this material. Now, if you take a typical aluminum alloy, for example, AL2024, you will see it has got 93.5% Al, and then there are some elements of copper, manganese, and magnesium present. Now, some of the parts are designed by steel, and this is about 15% of the structure. And these are the parts where high strength is required. So, steel has very good properties in terms of strength. So, for example, the landing gear, the engine fitting, the wing attachment fitting, and so on, these are coming from steel. And steel is also an alloy, it's built of iron and carbon. Now, titanium is also sometimes used in some parts. Its problem is that it's pretty expensive, so it costs 5 to 10 times the cost of Al or aluminum. But one of the advantages of titanium is that it retains strength at high temperature, and that's something which is beneficial in certain type of vehicles such as hypersonic vehicles or vehicles which are re-entering the Earth's atmosphere. Talking of hypersonics, there is one more material called Inconel, that is a nickel chromium based material, and this can withstand high temperature. So if you are interested in material science, there is a lot of research in this area, and continuous research keeps going on into these different type of materials. Now, let's just look at the different values of these materials in terms of the material properties or the mechanical properties. So, if we look at aluminum, for example, the Young's modulus is about 70 in this case, and we will see here that steel is much more stiffer here in terms of the Young's modulus in GPa. Now, if we look at the ultimate strengths also, we will see steel is very high, then we have titanium, then we have aluminum. And as far as density is concerned, the problem is steel is also highly dense, so its weight will be more. So generally what is done is that the aluminum wins out because of its superior stiffness to weight ratio. So the two things going here is that we want stiffness, but we also want low weight. So this is a particular characteristic which drives the aerospace vehicle material selection. We are not only concerned with the material having a high stiffness value, we are also concerned with the weight side of the equation. So that's something to keep in mind. Now let's look at one more material which is quite ubiquitous as far as aerospace is concerned, and that's composite materials. Composites are essentially made by combining two different aspects, which is the fibers and the matrix. So what happens is that it has been found that many material, for example glass fiber, have very high stiffness and strength properties. This also includes carbon fiber, boron fiber, and so on, but these are there only for the fiber. So actually if you take the bulk glass, the properties are not so good, but fibers are something which have very high stiffness and strength. So some people figured out that if you embed this fiber into some matrix, then you can use it for structural use. So the matrix which is typically used here could be polymers, it could be metals, it could be ceramics. So based on the kind of matrix you are using, you have polymer matrix composites, you have metal matrix composites, and you have ceramic matrix composites. So these are sometimes known by acronyms like PMC, MMC, and CMC. So do remember that. Now typically at lower temperature, polymer matrix composites will be most useful, but at some of the higher temperature applications, people often use ceramic matrix composites, and that will be something which you will use at high temperatures. Now let's look at some of the properties of the fibers. So for example, what happens with fibers is that the Young's modulus is pretty high, and also the strength of the fibers and so on is very high. So you will certainly recall that aluminum has E of 70, of about 70. So these are certainly quite high relative to that. So the way the composites are set up, for example, if you take the laminated type of composites, is that you have several plies or lamina which are put on top or put like this, and then you get what is known as a laminate. So essentially a bunch of laminas constitute a laminate, and these laminas or plies are actually very thin. And what happens is that each of these plies has a certain direction in terms of the fiber. So here I have given this kind of direction. So this would be something like 45 degree. If I have it like this, it would be 0 degree, and so on. And when we combine plies which are different, so we may have a 0 degree ply here, we may have a 45 degree ply, we may have a minus 45 degree ply, and these are known as the angles of the ply. And so the fibers are here, the matrix is the gross material which is here. And one of the things we can do is that by giving different ply angles, we can tailor the composite for application. So better stiffness to weight and strength ratio can be obtained, and you can even do something known as tailoring. So tailoring can sometimes help in situations like such as creating an aircraft which does not encounter instability problem, because you can create various type of bending, torsion, couplings, and so on. So you could, for example, design an aircraft which has a forward swept wing using some of these composites and still have it to be stable. So let's look at some properties of composites and compare it with the typical metals such as aluminum. And you can clearly see here that if we look at carbon epoxy, boron, glass epoxy, and so on, all these are pretty competitive, and most of them have much higher strength values. So this is something to keep in mind. The densities are also very competitive. So because of this, composite materials have become pretty popular as far as aerospace applications are concerned. They do have much better strength properties and so on, but I should also mention that they are somewhat more complex. They have multiple levels of failure mechanisms, and so one has to keep some of these things in mind. Now, if we look at the typical stress strain diagram for composites versus metals, we'll see composites have a very straight line type of curve here compared to metal, and so they have an yield stress and then they fracture. So essentially they have an ultimate stress out here. And if we look at typical metals, they go through yield stress, then they have ultimate stress, and then they have fracture here. So typically you use metal in this region, and normally the composite would have a higher level of stiffness compared to most metals out there. Now, beside this kind of strength-based thinking, we also have a problem known as fatigue, which takes place in materials. So if you take a certain metal or any material and you impose cyclic stress on it, then what will happen is that if you keep subjecting it to these cycles, it will break after many cycles. So especially many materials such as those subject to cycles because of rotating machinery, or it may be that an airplane is just taking off, landing all the time and going through these kind of things which are very large in number over a period of few years, then it is essentially being subject to this kind of cyclic loading. So in that case, what happens is that the maximum stress of the cycle can be taken and then it can be plotted like this. So maximum stress of the cyclic loading which you have given it, if plotted like this, after a certain number of cycles, it's going to fail. And that is known as the fatigue failure of the material, and that cycles which you get from experiments will be the point at which the material has failed. So you need to know the cyclic and fatigue properties of the material also. It's not just enough to know the ultimate strength and so on from the static tests. So in most companies, they do a lot of fatigue testing of different materials to know where exactly they fail. There are various rules also regarding fatigue as far as certification is concerned. So let's summarize today's lecture. We saw that flight vehicle structures have a issue that they need materials and structures which have high stiffness to weight ratio. So this is something very important to remember. There is a very favorite question in many interview panels as to why steel is not used in the different aircraft structures because it's so good in terms of stiffness, and the answer is because it's also much more denser, so you are not getting the benefit of high stiffness to weight ratio. Also, we see that a typical wing structure has to simultaneously carry axial bending and torsion loads, and so we need to design somewhat complex sections for it. It cannot be a simple beam, or it cannot be a simple rod, or it cannot be a shaft. It's some combination of these things which comes out in the typical multi-cell cross section and a box beam type of design. And also we saw that aluminum is the metal of choice as far as aerospace construction is concerned, but composites are becoming more and more widespread, and most of the modern planes such as the Airbus A350 or the Boeing 787 are essentially made of lot of composites. So over 50% of these aircraft can sometimes be composite materials because not only they have excellent stiffness to weight ratio, they also have very good fatigue characteristics and also damage tolerant characteristics and so on. So that was the lecture which introduced you to structures and materials. And the next class I will talk a little bit more. We will discuss stress and strain, and we'll look at how the stress and strain are related in a more generalized sense for a three-dimensional problem. So we'll move from one dimension, which we saw here for the rod, to the three-dimensional case, and from that we are going to be able to define certain things about different materials, such as what are orthotropic materials, what are isotropic materials, and what is the Young's modulus and also the Poisson ratio. Today in some of the tables I showed that parameter mu, or rather nu, and I did not discuss it much, so we will show the genesis of that parameter in our next lecture. So I'll end this lecture now and I will see you in my next lecture. See you then.